Have you ever really stopped to think about what keeps our digital world from falling apart? Well, we're about to dive deep into one of the unsung heroes of digital security, the cryptographic hash function. This is the magic behind things like secure signatures and making sure your files haven't been tampered with. The best way to think about it? It's like a unique digital fingerprint for any piece of data.
So why do we even need these things? Okay, picture this. You've got a massive file, say 256 megabytes, and you need to sign it to prove it's authentic. Now, the naive way to do this would be to sign every little piece of the file separately. But if you do that, you're going to have a bad time. You run into some massive problems, like right away. And this slide really lays out the nightmare. First off, the sheer amount of work is insane. We're talking about performing 1 million separate, heavy-duty mathematical operations just to sign one file. Then you've got the data problem. You'd have to send your 256 meg file plus another 256 megs of signatures. You've just doubled your bandwidth for no good reason. And the craziest part? It's not even that secure. An attacker could just delete blocks or shuffle them around, and the individual signatures would still check out. It's a complete mess.
So what's the fix? Well, it's actually an incredibly elegant solution. Instead of signing 1 million different chunks of a huge message, what if you could just sign one single tiny thing that represents the whole file? That tiny thing, that's our digest. That's the hash. A hash function is basically a magic meat grinder for data. You can throw anything into it, a single word, a picture, that entire 256 megabyte file, and it spits out a short, perfectly sized string of characters. That output is its unique digital fingerprint. And here's the kicker. If you change just one single bit of the input, the fingerprint changes completely. It's totally unrecognizable.
So let's see how this makes everything work, using our friends Alice and Bob. First, Alice takes her message and runs it through the hash function to get that tiny digest. Then, and this is the important part, she uses her private key to sign only the digest. She sends the original, big message and that tiny little signature over to Bob. Now Bob takes the message he got and runs it through the exact same hash function on his end. Then, he uses Alice's public key to unlock her signature, which shows him the hash she started with. If the hash he just made matches the one from Alice's signature, boom, he knows for a fact it came from her, and that nothing was changed along the way. So much cleaner, right?
Okay, but you can't just use any old formula for this. To be considered cryptographically secure, a hash function has to play by 3 very, very strict rules. These are non-negotiable.
Rule number 1 is that it has to be a one-way street. We call this Preimage Resistance. It means that if I give you a digital fingerprint, it has to be practically impossible for you to figure out what original data created it. You can't work backward from the hash to the message. Rule number 2 is second Preimage Resistance. This is all about preventing forgery. It means if I have a document and it's hash, you shouldn't be able to come up with a different, maybe fraudulent document that just so happens to have the exact same hash. And then there's the third rule, the toughest of them all, collision resistance. This says it should be impossible to find any 2 different messages, any pair, out of all the possibilities in the universe that accidentally produce the same hash. This is the property that usually gets broken first. And that difficulty leads us to something, well, it's just plain weird. It's a counterintuitive weakness in probability that affects hash functions. And it all starts with a simple question about a birthday party. So let me ask you, how many people do you need in a room to get a 50-50 chance that at least 2 of them share a birthday? Now, your gut might say, I don't know, half of 365, so maybe 183? But that is way, way off. The answer is just 23. Yeah, that's it. With only 23 people, it's already a coin toss whether 2 of them share a birthday. It's called the birthday paradox, not because it's a real paradox, but because it just feels so wrong to our intuition. So what in the world does this have to do with hacking? Well, this exact principle is used in what's called a birthday attack. An attacker trying to find a collision doesn't need to create a fraudulent document that matches a specific hash. No, they just need to generate tons of variations until they find any 2 that happen to collide. It's just like the birthday problem. Finding 2 people with the same birthday is way easier than finding someone with your specific birthday. It dramatically reduces the amount of work an attacker has to do. So, how do we fight back against this weird mathematical quirk? The defense is pretty simple, actually. Just make the hashes longer. You're basically making the room of possible birthdays way, way bigger. To get what we consider a practical security level of about 80 bits, you actually need the hash output to be twice as long, at least 160 bits, to make finding a random collision hard enough. This whole situation, this constant battle between stronger math and cleverer attacks, has basically created an arms race over the years. Old algorithms that we thought were secure are shown to be weak, and they have to be replaced by new, stronger ones. And you can see that history right here. MD5, with its 128-bit output, is totally broken. Just don't use it. It's dead. SHA-1, at 160 bits, had a long run, but we now know it has critical weaknesses, so it's being retired everywhere. The current king of the hill is the SHA-2 family. It gives you much longer outputs, anywhere from 224 to 512 bits, which keeps it safe from these kinds of attacks for now. All right, we've covered a lot of ground. So what are the big, important lessons you should really take away from all this? Okay, here's the bottom line. Hashes are absolutely vital for making digital signatures work efficiently. A secure hash has to follow those 3 golden rules: one way, second preimage resistant, and collision resistant. You should never ever use MD5, and you need to be migrating away from SHA-1 as soon as possible. For any modern system, you should be using something from the SHA-2 family. And you know what? If you're building something that needs to be secure for a long time, aim for a hash output of 256 bits or more. And all this leaves us with one last big question to think about. The security of all these algorithms we use today is based on the idea that certain problems are just too hard for computers to solve in a reasonable amount of time. But our computers are getting exponentially faster. We've got things like quantum computing on the horizon. So it really makes you wonder, how long can any code that we call unbreakable today truly last?